Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems. Propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems. Airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
Instrumentation.
Go.
COM.
Go.
Timer.
Go.
GCQ.
Go.
Umbilicals.
Go.
ECS.
Go.
Facilities.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
AC is go.
Range coordinator.
Clear to proceed.
Launch director.
You have permission to launch.
Proceeding with the count. T0 is planned for 18:30:33 Zulu. Set count to start at 18:26:33 Zulu.
Roger. T0 is set for 18:30:33 Zulu. Count will start at 18:26.
Polling is complete and the team has given the go for launch. From T-minus 4 minutes until launch, you'll be listening to Doug Lebo and his team performing the final steps in the countdown procedure. You'll hear the team confirm securing of Atlas liquid oxygen topping, followed by the call to transfer the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 1 minute 55 seconds, the team will command the launch sequencer to start, followed shortly by securing the Centaur liquid hydrogen and liquid oxygen topping activity. At T-minus 1 minute 40 seconds, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed by verification of the Centaur tank pressures. A final status check of Atlas, Centaur, and WorldView-4 readiness happens at T-minus 25 seconds. Seconds before liftoff, the RD-180 engine ignites and performs a health check before lifting the vehicle off the pad. After liftoff, you'll hear the voice of Marty Malinowski providing us with flight commentary.
On my mark, the time will be T-minus 4 minutes and counting. 3, 2, 1, mark. T-minus 4 minutes and counting. 3:55.
Ground power is enabled.
The countdown clock has resumed and we are go for launch at 10:30:33 Pacific Time.
Three.
Securing Atlas LO2 topping.
250.
Atlas tanks to flight pressure.
FPS internal.
$159.
Vehicle internal.
$155.
Launch sequencer start.
150.
Securing Centaur LH2.
Securing Centaur LO2.
140.
Launch enabled.
137.
FPS armed.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and western range are go for launch.
120.
Orca's armed.
FCS count started.
110.
Vent valves locked.
This is a Rock. Range is green.
Copy, Rock.
1 minute.
T-minus 1 minute.
.40.
Stable at step 3.
T-minus 30 seconds.
25.
Status check.
Go Atlas.
Go Centaur.
Go WorldView-4.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have RD-180 ignition, and we have liftoff of the United Launch Alliance Atlas V rocket carrying WorldView-4 for DigitalGlobe, doubling the capacity of the world's highest resolution imaging satellite constellation and allowing everyone to see a better world.
We have experienced a loss of data and now has resumed. Currently completing the pitch yaw roll program.
You're hearing the voice of Marty Malinowski
And
providing
pitch yaw
launch
roll
vehicle
program
ascent
has
data.
completed. Now flying the zoom 0 angle back phase of flight. RD-180 performance looks very good at this point. Mach 1. Up on maximum dynamic pressure. Now have passed max Q. RD-180 performance continues to look good. Body rates are controlling down the middle. Booster has throttled back, right on schedule. Signatures look good. Current altitude is 11. Copy that as 13 miles. Downrange distance 5.3 miles. Current velocity 1,659 miles per hour. RD-180 continues to perform well. Injector pressures look good, as well as M2 pump speed. LH2 tank vent is underway. I have begun Q alpha limited steering at this point, and the vehicle is now 50% of its liftoff weight. RD continues to perform well. Coming RCS pyro valve. That pyro valve has now fired. System is pressurizing to flight levels, and signatures look good. Current altitude is 31 miles, downrange distance 35 miles, current velocity 3,760 miles per hour. And we've completed the Q alpha limited steering at this point. Body rates continue to look good. Booster engine continues to perform well. Pump speeds, injector pressure, all on band. Booster is now 1/4 of its liftoff weight. Booster has begun to throttle to maintain 5 Gs, constant acceleration. Space cooldown is underway. Now begun throttling to 4.6 Gs in preparation for go. Boost phase cooldown is complete. And we have engine shutdown. Beagle looks good. Have indication of a clean stage separation. Box and fuel restart on the RL10. And 2 purge firing. The RCS is underway. Have ignition and full thrust on the RL10. Up on fuel frame jettison. We have indication of a clean jettison. That looks good. Current altitude is 133 miles, downrange distance 263 miles, current velocity 9,768 miles per hour. Centaur PU is currently in its fixed angle position for the early portion of this 11-minute and 16-second burn. RL10 performance looks good. Chamber pressure, LOX pump, and fuel venturi all on band.
This is Atlas Mission Control at T plus 5 minutes, 28 seconds. We've just seen the successful liftoff of the Atlas V rocket carrying WorldView-4 for DigitalGlobe. All systems continue to operate nominally. Our next event, cutoff of the Centaur engine, is scheduled to take place in approximately 11 minutes. So I'm joined now by Tanir Kadanas, DigitalGlobe's Director of Industry Leadership.
It's great to be here, Matt.
Well, it's great to have you here, Tanir. So we know that rocket launches and satellites fascinate people, both young and old.
Absolutely.
And I know DigitalGlobe did ask some kids to submit some questions about launches, satellites, things like that. So are you ready to take a few of those, see what we got?
I think I am.
All right, great. Let's take a look and see what our first question is. So 9-year-old Colin has asked us, how big is the satellite and what does it weigh?
So WorldView-4 is almost 18 feet tall and 8 feet wide. That's about the size of a small playground that has a swing set and monkey bars and a slide, or more like probably the size of a pickup truck, like a Ford F-150. Now, at launch, the satellite weighs about 5,200 pounds or 2.6 tons. That includes approximately 1,000 pounds of fuel. So for comparison, I would say it weighs about as much as an adult elephant does.
Great, good answer there for Colin. Thanks. Let's take a look at our next question that we've got here. Our next question comes from Anthony, who's 14, and he wants to know, what is the lifespan of a satellite?
Well, unfortunately, they don't last forever. So in this case, WorldView-4 will be on orbit about 10 to 12 years.
Okay. Let's see. The next question that we got has come in from 13-year-old Oliver, and Oliver wants to know, how fast will the satellite travel?
Flies pretty fast. It's going at 17,000 miles per hour. For comparison, if Oliver's mom or dad were driving down the highway at 65 miles an hour, the satellite is traveling almost 262 times as fast as that car is going down the highway.
It's pretty fast.
It is. It is.
All right. Let's see. We had one other question come in from Oliver, and Oliver also wants to know, how many people worked on the satellite?
You know, that's a hard number to estimate because there's been 4 main companies involved with building it and almost 20 subcontractors. So I would say from DigitalGlobe, we estimate that as many as 400 people probably were involved in getting WorldView-4 ready.
It's amazing, between the rocket, the satellites, everything that takes place, how many people actually put their hands
It's a tremendous
on
effort.
it. It really is.
It's a tremendous effort.
All right, let's take a look at our next question here. Our next question comes from 10-year-old Evan, who wants to know how you charge the batteries on WorldView-4.
It does indeed have batteries to charge. So the satellite, though, has 5 solar panels. Each panel is about 9 feet by 4 feet wide. The panels together produce about 3.5 kilowatts of energy when it's in full sunshine, which is enough to power a small house, for example. In addition to the panels powering the satellite when it's in full sunshine, they're also charging the batteries at the same time so that the satellite can actually operate when it's on the dark side of the Earth, which is about 30 minutes during each orbit.
Makes sense. All right. Let's see. The next question is coming from 6-year-old Ben, and Ben wants to know, does the satellite see Pluto and other planets in outer space?
Again, a great question. So WorldView-4 does have the capability to see planets. Now, we would obviously need to turn the satellite around to face outer space instead of Earth in order to see them. But we did check with one of our satellite engineers, and he thought Pluto would probably be too far away to see. But I think we could definitely see other planets like Mars, Venus, probably even Jupiter as well.
Yeah, as long as you could turn it around.
Exactly. Exactly.
All right, let's look at our next question here that's come in from Kenzie, who's 12, and wants to know if it's really hard to make a satellite or if you've cracked the code and it's really easy now.
Well, there's a saying around DigitalGlobe that space is hard. So we talked to two of our satellite engineers who worked on building WorldView-4 to answer Kenzie's questions. They both agreed that building satellites is hard, even though we've successfully launched, obviously, several into space. One said that, rocket science is easy since physics and the equations have been around fully for 200 years. But, Matt, you're the rocket engineer and you understand this much better than I do. It's hard, right?
Absolutely. Rocket science is hard. You've got gravity to deal with, you've got space to deal with, and all those are very unforgiving. And unlike things that you work on here on Earth, once we launch that rocket, you don't have a chance to go change things, right? You can't pull your car over to the side of the road and tweak some things.
Exactly.
So it's the amount of focus that has to go into the manufacturing processes, the engineering processes to make sure that you have the right craftsmanship in that rocket. It's astounding the amount of quality that has to go into it.
So, and to build on what you just said, our other engineer actually quoted NASA's Flight Controller's Creed, which states that there's no substitute for total preparation and complete dedication, for space will not tolerate the careless and indifferent. And he said that, this is still true, even though we have so much more technological advancement these days.
Absolutely. We do these one at a time, and each one has its own unique challenges.
Exactly.
All right, that's a great question. Let's take a look at our next question from 7-year-old Landon. And he really has a great question. How much fire does it take to lift a rocket into space?
Well, I know that unlike our cars, the Atlas V rocket doesn't use gasoline. Instead, each of the two stages of the rocket use a mixture of high-tech fuel and oxidizer, right?
Yeah, absolutely. So for the Atlas V booster, we use a highly refined kerosene called Rocket Propellant 1 or RP1 as the fuel. And then we have liquid oxygen that's chilled down to minus 298 degrees. For our oxidizer. So you mix those things together to get fire out of the booster. And for our Centaur upper stage, we have liquid hydrogen at minus 423 degrees mixed with that liquid oxygen. So very cold propellants that we have to use to be able to get the fire that we need to get the rocket where it needs to go.
And to make that fire, the Atlas booster tanks hold about 25,000 gallons of RP1 that you mentioned. That's probably the equivalent of about 400,000 cups of coffee. And then there's almost 50,000 gallons of liquid oxygen, and that's over 500,000 cans of soda for comparison. Now, the Centaur unit, the second stage that we talked about, those tanks hold about 3,000 gallons of liquid hydrogen and about 4,300 gallons of liquid oxygen.
Yeah, it's a lot of very cold fuel to get us where we need to go.
Indeed.
All right, let's take a look at our next question. 3-year-old Bryn wants to know if the rocket is pink.
Well, let me answer this way. There are three main sections of the rocket. So the first stage that we talked about, the booster, it's coated with a copper color so that it can prevent rust. The second stage, called the Centaur that we mentioned, is painted white. And finally, the payload fairing, which holds the WorldView-4 satellite, that's painted white as well. But Matt, when we've seen the rocket go off, that copper-coated section is white at liftoff. Why is that?
Yeah, absolutely. So we talked about that really cold liquid oxygen in that booster tank, and with that very cold tank there, it'll pull the moisture out of the air. It'll freeze just a thin layer of frost, and that's why you get a white-looking rocket on the booster at liftoff.
There you go.
So yeah, good question about the colors that we see when we lift off. All right, let's see. That's a great question. Let's look at our next one here from Evan. Why does the rocket not keep going straight away from the Earth?
So the rocket launches straight up as we just saw, but eventually it takes a curved path to get the satellite into a circular orbit around Earth. Also, once the boosters stop pushing the rocket and the satellite up, the Earth's gravitational force begins to pull it down. And so it doesn't keep going into space, obviously.
Makes sense. See, next question came in, I believe, from 12-year-old Buck, who would like to know at what altitude is the engine or booster ejected?
That's a really good question. Sounds like Buck may want to be a rocket engineer like you someday. The rocket Centaur upper stage separates from the Atlas V booster at about 4 minutes and 9 seconds, and at that time it's around 84 nautical miles from above the surface of the Earth. Now, after separation, the booster stage actually falls back to Earth and splashes into the Pacific Ocean.
It's great. That was what we just saw from today's launch. We had that fantastic video showing us that today. All right, let's look at the next question here from 3-year-old Liam, who wants to know how far into space the satellite will go.
So the satellite will orbit 383 miles above the surface of the Earth. For comparison, I think we saw this earlier in the video. That's like driving from one end of Florida to the other.
Yep, a ways away.
Yeah.
Let's see. And then last but not least, we have 4-year-old Mila, who would like to know if there are people on the rocket, maybe somebody like Curious George.
Well, nope. Sadly, Curious George isn't on board, and neither is probably the man with the yellow hat.
That's too bad. I know my my 6-year-old son would think that'd be pretty interesting.
Yeah.
So, Tanir, thank you so much. Great job answering those questions.
Thanks, Matt. That was really fun.
It really was. All right, so let's go ahead and get back to the mission now. We'll come back again and get a chance to chat in a few minutes.
Great.
Had some momentary data recovery there. Levels look good. Still in a blackout at this point. At this point, Centaur should be orbital. Data has resumed. RL10 performance, very good. Audio rates going down the middle.
Main engine, let's listen in to Marty
On MECO.
Malinowski.
And we have indication of MECO. Shutdown looks good. Have gone to 4S settling. Done the turn. Separation attitude.
We just heard confirmation of the successful cutoff of the Centaur main engine. Our next event is WorldView-4 separation, scheduled to take place in about 3 minutes. Once again, here's Marty Malinowski.
Our fuel tank has vented down as planned. Levels are stable at this point. Continuing our turn to spacecraft separation attitude. Throttle pressures are stable. Batteries are as well. And we have the MECO 1+3 OPM showing all parameters very close to pre-flight predicted actual. Right on schedule for the planned orbit. And Centaur fuel tank has been vented down again. Levels are stable. During completion of the spacecraft separation attitude turn. And we have completed the turn to spacecraft separation attitude. In RCS fairings. And we have indication of spacecraft separation.
This is Atlas Mission Control at T plus 19 minutes, 56 seconds. We've just seen the successful WorldView-4 delivery to orbit for DigitalGlobe. I'm joined once again by DigitalGlobe's Tanir Kadanes. Tanir, congratulations on a successful launch today and our delivery to orbit.
Thanks, Matt. This is truly an exciting time for all of us.
It really is. So we saw a video earlier about how DigitalGlobe's imagery helped free slaves on fishing boats in the South Pacific. Your company's regularly involved in events all around the world.
That's right, Matt. But before I answer your question, though, I just want to share with the audience that for the fishing slavery AP story, Martha Mendoza and her team at the AP won the Pulitzer Prize for public service, which was just, an amazing, amazing accomplishment. But back to your question, yeah, many people don't know it, but our satellite imagery is a part of everyday life. For example, global development organizations use our images and big data analytics for things like figuring out how many people need polio vaccines in each community that they will visit. It helped eradicate polio from Africa 2 years ago, and now that a few more cases have been popping up in Nigeria, we're working on analyzing the latest imagery and providing support for vaccines out there. Also, when Ebola was rapidly spreading through Africa, there weren't detailed maps available, so aid groups didn't know what roads existed for them to move medical supplies, or where there would be obstructions for helicopters, or even where helicopters could land. All of this posed major challenges to getting to people who had Ebola. There were even some villages that weren't even on the map, so they wouldn't have even gotten treatment if we hadn't found them with our satellites. We used a combination of imagery and analytics to map these affected areas, leading to a much quicker response for the outbreaks.
I mean, the impact in the world really is astounding of what this kind of imagery can do.
Exactly. Another instance, first responders benefit from our shortwave infrared sensors on a satellite to see through smoke in wildfires like these that you see in Fort McMurray wildfire in Canada this past summer. As you can tell, it lets them see exactly where the fire is burning, so they know which homes have already burned, which ones can still be saved, and where to send firefighters. We in fact used these same capabilities in September when a wildfire started right here at Vandenberg Air Force Base when we tried to launch WorldView-4 earlier. We imaged the base and shared the results with firefighters, and it definitely helped WorldView-4 stay safe inside within the Atlas V rocket.
Yeah, we were both here just a couple months ago and saw the impact of that wildfire, and it's amazing to see those images that we're able to keep launch pads and people safe throughout that whole experience.
In addition, this past summer, our satellite constellation was imaging Rio de Janeiro on a daily basis ahead of the Summer Olympics in preparation for security teams to have the best materials for planning potential responses.
Yeah, I mean, those kinds of opportunities from a security perspective and being able to have that insight has to be huge.
Yeah, and our imagery is also leading to greater global transparency, which we need these days. We're tracking, for example, the Spratly Islands in the South China Sea. China is building those islands in disputed territory, and it's causing a lot of political tension in that part of the world. Our images show that China continues to make those islands bigger, and they're adding buildings that are large enough to hold planes and strips of concrete that could be used as runways.
Yeah, obviously, having that insight all over the world. We saw the earlier stories. Obviously, at a world event level, that gives us some insight. How about more at a day-to-day level, what people might experience?
Well, the average person uses our imagery on their computers and phones when they look at Google, Apple, Bing Maps, in satellite view. Now, you wouldn't know it's our imagery unless you looked really closely, at the fine print in the corner. But now we have app developers that are coming to us looking to use our imagery in their apps because they're looking for the most accurate location data available. It's really neat to see how creative they're being with the use of our imagery.
I mean, that's really a wide variety from world events to app developers to, just being able to pull up a Google image on your computer. It's really a wide variety of things. So I'm assuming you're also involved in what they call the Internet of Things or the gig economy?
Well, indeed, we are. Best example probably is Uber, that, as you know, is revolutionizing transportation and making the experience incredibly easy for all of us. At DigitalGlobe, though, we're thrilled to be joining them in that revolution. Our partnership with Uber is to supply high-resolution satellite imagery, which will help improve the Uber experience for riders and drivers alike. Specifically, Uber will leverage our industry-leading high-resolution imagery to access location intelligence and to help identify and improve both drop-off and pick-up locations.
Well, Tanir, congratulations again on today's launch. I really look forward to what we're going to learn from WorldView-4, and it was really a pleasure having you here today.
It was my pleasure, too. Thanks so much, Matt.
Thanks. Really appreciate it.